So conditional operators. We pretty much know what these mean. Double, double, equal means you're comparing two values to see if they're the same. And if they are the same, then it evaluates to true. Otherwise, it evaluates to false. Not equal is just the opposite. Greater than, less than, greater than or equal to, less than or equal to. There's only one point that really needs to be made about that, because I know that, I've taken math courses and know what greater than and less than mean. If you have this, x is less than 3, the opposite of that is not x greater than 3. And so what if x exactly equal 3? Say that's the true case. So, is x less than 3? No, it's not. Why did I type true? It's not. So is x greater than 3? It's still not true. 3 is not greater than 3. So these are not, in fact, opposites. Greater than is not the opposite of less than. To get them to be opposite, you have to do that. Greater than or equal to. Then it's true. So if you're at the edge case, if you're at the case where the number equals the value that you're comparing against, that's where things could go awry. That's where you need to make absolutely sure that you either need to use, or when you're going to use less than or equal to, or greater than equal to. So these are the opposites. Right? So less than, its opposite is greater than equal to. Greater than, its opposite is less than or equal to. And equal to, its opposite is not equal to. Less than is not the opposite of greater than, for reasons explained. X less than 3 is not the opposite of x greater than 3. Try the logic out in your head. So the opposite of x less than 3 is what? X greater than or equal to 3. That makes sense? Okay. So the expression result. Yeah. I mean, if I wanted to, I could, hide this over here. Is 5 equal to 5? Yeah. Is 5 not equal to 5? Well, that's the opposite of this. So if this is true, then what's this going to be? False. Is 5 greater than 5? No. Is 5 less than 5? No. Is 5 greater than or equal to 5? Yeah, because they're the same. And is 5 less than or equal to 5? So those last two are true. These three are false, because if you check to see if 5 is different than 5, it's going to say false. Opposites. So if structures. In fundamentals, we call this a dual alternative selection. We want to give it a fancy name. Dual alternative selections, what that textbook called it. Why is it called dual alternative? Because it does one thing or another. Right? If the temperature is greater than 80, turn the AC on, else turn the AC off. Now, that would just cause it to, flicker between on and off as it bounced between 79 and 80. Not too efficient, but whatever. Okay. So, it's either going to do one thing based on this condition, whether this is true, it does one thing. If it's not true, it jumps down to the else and it does the other thing. So, there's two alternatives. If it looked like this, that would be a single alternative. There's no else. So it's either do something or nothing. If the temperature is greater than 80, we turn the AC on. Well, we never turn it off. Maybe we turn it off somewhere else, but not part of this if statement. So it's either something or nothing. And the nothing is called called the null case. The null case is if the temperature was not greater than or equal to 80, then don't do anything. we have also available to us some logical operators and an or. In Python, you've got to use those words. You use the word and you use the word or, but in a lot of other languages, including C and C++ and Java, you use the symbol, two ampersands. That means and, the shift to the 7. And for or, you use two vertical bars with the shift backslash, which is the key above the enter key. And so you word it like this, right? If hunger is greater than 0 and money greater than 0, right? We're going to go out to eat. Printf, let's go eat. Except, since this is not Python, we replace it with that. So if the hunger is greater than 0, if we're hungry and we have money, we're going to go out to eat. We might throw in a dual alternative. Else, print, nah, let's stay home. Right? You might be hungry, but you don't have any money. I guess you don't have a friend to mooch off, so you're going to stay home. So, and both sides have to be true. Let's see how they state that. See if they state it in a better way. Okay, not at all. All right, so I get to make it up myself. And requires both sides to be true, both sides of the operator. Technically, we would say that those are the operands. But it's kind of weird to think about this entire expression here as being an operand, and this entire expression being an operand. But that is actually the case, because this evaluates to either true or false, and this evaluates to either true or false, and then we have two operands which can be used to settle the and. So, and requires both sides of the operator to be true, or only requires one or the other. And if they both are true, so much the better. Like this. If sick is greater than 0 or tired is greater than 0. If we're either sick or tired, we get to stay home from work. Printf, stay home from work. That must have a nice job in order to be able to stay home just because we're tired. And if we're sick and tired, even better, right? We have two reasons to stay home. But that's an or, right? We can stay home if we're sick. We can stay home if we're tired. Whereas this one, the and, means that we go out to eat only when we have hunger and we have money. Hope that makes sense. So they show what's known as a truth table. The truth table looks like this. Just pretend there's the word and between those two things. Right? Come on. Like that. And pretend the word or is between these two things. So for an and to be true, both sides have to be true. So false or false, neither side are true, so the result is false. False or true, excuse me, false and true, well, both sides have to be true, so it's still false. True and false, they both had to be true and they weren't, so it's false. True and true, okay, that's the only time that they're both true, and so that's the only time the result is true. Notice the way that it's set up. Usually I do the false and the false at the top and the true at the bottom, but anyways, notice the way that it's set up. There's only one time when the result is true, and that's when both sides are true. So how about false? Only if either side, if one side or the other is true, then the result's going to be true. So false or false, well, neither side is true, so the result is false. False or true, well, one side is true, so that's a true. True or false, that's another one where one side is true, so that's a true. And true or true, well, even better. Both sides are true, so that's a true. So for and, the only time it's true is when both of them are true. Both sides are true. For or, the only time it's false is when both sides are false. I'm going to kind of show y'all something. See if this makes sense. So if we have x and y and we have a result, and so if we have false and false, we have false and true, we have true and false, and we have true and true. The only time that a result is true is when they're both true. The rest of them are false. Fake? No, false. I could change this a little bit and make it look like math. Say this is multiplied. So say that was 0 times 0, because ultimately a 0 is treated as a false and a non-zero is treated as a true. So what is 0 times 0? The result is 0. So here, that true is going to be a 1. So it's 0 times 1? Still a 0. How about this? If that's a 1 because that was a true, and this is a 0 because that's a false, what is 1 times 0? 0. And then now, since both of these are true, a 1 times 1 is a 1. So logically, logical AND is expressed in logical notation by multiplication. Now, not in programming, but if you ever go and take a logic course, a 4-year logic course, or you're getting a law degree or a computer science degree at a 4-year university or something like that, they will express logic as multiplication. X times y means x and y. So what about multiplication? Excuse me. What about or? How about this? False or false? Is that true or false? For or to work, only one side has to be true, one to the other. So that's a false, because neither side is true. How about false or true? That's a true, because one side of them is true. How about this one? That, yes, other side is true, so good to go. Here we're both true, even better. All right, now I'm going to copy this and replace it by addition, just like we did multiplication. And again, I'm going to replace all the F's with zeros and all the trues with ones. And I'm going to just delete these rather than give it. Okay. So 0 plus 0 is equal to 0. How about 0 plus 1? Obviously, 0 plus 1 is equal to 1. 1 plus 0. 1. 1 plus 1. Well, you know, we would say 2. But in Boolean logic, there's only trues and falses. So there's only zeros and non-zeros. So really, it's 1. If you look, it's the same, right? 0, 1, 1, 1, false, true, true, true. So, and is same thing as logical multiplication, or is the same as logical addition. If you can't remember your truth table, if you can think that and means multiply and or means add, I don't know which is easier to remember. I would just remember that if both sides are true, then an and is true. And or means only one side or the other has to be true to get the result to be true. If you can remember that, so much the better. So truth table for the not operator. Well, not x, if x was true, not x is false. And if x is false, then not x is true. And so the not operator is the exclamation mark. So what did we say and was? What's our special symbol for and? Ampersand. or vertical bars, shift backslash. Now single ampersand and single vertical bar also mean something, but it's not logical. Not a logical operator, it's a math operator. We could talk about it, but I'm tired of talking about bits with y'all for now, so we're going to skip that. All right, so here we go. We have these symbols, and we can make statements with them to chain conditions with them. One last thing to remember, though, is that if an AND is multiplication and OR is addition, well, which has higher precedence, multiplication or addition? What is higher priority? Yeah, multiplication is higher priority. That makes sense? Now I'm looking at you.
Because of order of operation.
Right, because of order of operation. Right, so order of operation, since star is higher than plus, and is higher than OR. Let's get Visual Studio going. Although, since you don't have it installed yet. Anyways, you could use the online visuals. You could use an online C++ compiler. Yeah, online C++ compiler. Just choose the top one or whichever. We're good to go. Okay. So file new. In fact, it's even better because it's already got some of the boilerplate built in. Howsoever, it's got C++ boilerplate, not C boilerplate. So this is lecture G. Make sure I remember which directory it's stored in. Mine is in my name / documents. Empty project. View Solution Explorer. Right click, add a new item. Lecture G.C. Gonna go and grab my boilerplate. Added a few things to it. So if you haven't added this stuff, you may as well add it right now and save it. What did we add? We wanted string and math and std lib. And also we disabled a warning. Remind me what that one did. Pragma warning disable, what was it? 4477? Let's Google that one up, remind ourselves what it was. I think that was the use of double versus float. We really ought to find a way of fixing it rather than disable it. Yeah, we're going to try to fix it, so I don't actually want to put that one in there. You can leave it there and comment it out, but we'd rather try to fix it next time. What causes 4477 is if we do something like this. Double D equals 3.1, whatever. And then we try to print it out, and we print it out as %F. Like that. We may get a warning out of it. Ow, for Pete's sake, I didn't put that in my code. I really don't want that in my boilerplate. Let me undo all those changes. Let me leave that one. All right. Didn't seem to print it out. Oh, my print statement's gone. I guess I undid everything. Alright, once more with feeling. Double D is equal to 3, 3.1, whatever. Printf parentheses, quote, percent F for floating point, backslash N, end quote, comma D. I should get a warning because I'm trying to print a double inside a float, and a double is double wide over a float. So if I come over to error list, I'm okay, fine. No, that actually should fix it if the error was occurring and I uncommented it out. Alright, well, seems to be working now. Maybe it was for scanf. I think that was it. How about scanf, parentheses, quote, percent F, in parentheses, comma D, ampersand D. That's the syntax for scanning. The ampersand goes in front of the D, excuse me. Once more. Now it wants me to type in something. Alright, okay. Check our error list now. One warning. Okay, there we go. There's our one warning. And it says the format %f requires an argument of type float. So what we really need to do is, since it's a long float, since it's a double wide float, we need to do %lf there. And if we do that, we don't get that warning. So I'm just going to add a comment up to the top. Remember to use scanf %lf when reading a double to get rid of warning 4477. Now I'm going to delete this stuff. Now that we've proven the point. Or maybe I'll just make it comments. Yeah, why not? Cut that, paste it, make it comments. Alright. It's my boilerplate as it exists right now. I mean, not really. This stuff's not in there. But I got rid of 4477. Okay, so what are we going to do? We're going to check to see if somebody is of age and they are a citizen. And if they are of age and they are a citizen, then they can get licensed to vote. They can get a voter registration. So let's do this. Int age, int citizen, and I'm just going to put a note here that 1 means yes, 2 means no. So we could ask for the age. We'd have to type it in every single time we run the program. Why don't we just fake it for now? So age is equal to 30. Citizen equals 1. They are a citizen. And now we're going to write an if statement. And if they're a citizen, then we're going to tell them, if both of those are true, we're going to tell them to go register to vote. So if age is greater than or equal to 18, I believe that's the limit, and then ampersand, ampersand, citizen equals 1, close parentheses, curly brace, then printf, you can go register to vote. Period, backslash n, end quote, semicolon. Else we need to tell them that they can't. Else, curly brace, printf, unable to, or not qualified for voter registration. \n, parentheses, or end quote, in parentheses, semicolon. All right. The way we have the data set up right now, is it going to print register to vote or not qualified? It is going to print register to vote because both of these are true. Yep. Howsoever, if there's 17 and they're not a citizen, not qualified, well, yeah, that makes sense. They didn't meet either criteria. What if they're old enough, but they're not a citizen? So this is true, but this isn't. So it's still going to do the false thing, the else. Not qualified. We could have worded this differently. We could say, if age is less than 18 or citizen equals 0, not qualified. We're kind of flipping the logic, right? We're going to use an or, and we're going to check for the opposites. So if parentheses age less than 18, because this is the opposite of this, or citizen equals 0, they're not a citizen, end parentheses, curly brace, close curly brace, printf. Hopefully you will in the future. \n, end quote, end parentheses, semicolon. Wish I could free up a little bit of space here, right? I don't need that much space for my line numbers. Oh well. Okay, so we have expressed the opposite here. The way we express the opposite is we changed and to or, and we flipped the way these two things were worded. There's a name for that logic law, and I've forgotten it. That if you want to express the opposite of something, ands become ors, or vice versa. So, if our age is less than 18, it's a problem. If we're not a citizen, it's a problem. If both are true, then it's certainly... Wait, did I say? Yeah. If age is less than 18, it's a problem. If citizen is equal to 0, it's a problem. And if both of them are true, so much the worse, it's a problem. And so not qualified for voter registration. Oh, but it didn't print my second message. Oh, because I put it after pause, not before. I'm going to need to move my pause down. Sounds strange. Sounds like I'm a cat. Gonna move, cut my system pause, and paste it above the return. My mistake. Control V is in vehicle to paste. There we go. If you're using the Visual Studio Editor, and if you're using another editor like on the Mac or something, I bet this also is true. Notice these little minus signs. You can roll up your code. The only reason you roll up your code is to kind of shorten it on the screen so that you can just focus on the bigger picture. You can even roll up your entire function, right? If you have 10 different functions in the file, maybe you want to roll them all up. So that's and that's or. Now let's go ahead and put a else clause here as well. Else, curly brace, printf, it is a privilege to vote. Go do it. \n, end quote, end parentheses. Now there are other rules as well, right? You have to live in the state. You can't be a felon in most states, whatever. But we're keeping the example simple. So operator precedence. This is a much bigger chart. Still, parentheses, and then some stuff known as postfix notation, which we really haven't talked about yet since we haven't talked about arrays. Function calls. All right, and then unary. Well, we've talked about an unary subtraction, right, which is just a negative sign. Like if you type in -3, x equals -3, that means x, equals 3, and then made negative, because that minus sign is not a number, it's a symbol. So good old arithmetic, multiplication. I wonder what the ... means. And anyways, I guess addition and subtraction have lower priority than arithmetic. Shifting, which we haven't talked about, might be fun to talk about. Relational inequalities, and then bitwise, which I mentioned and didn't explain. Logical, ands and ors, a conditional, and an assignment. So assignments are way down at the bottom. Why are they way down at the bottom of the operator precedence? So that if you do something like this, A is equal to B plus C. Since equal is the lowest precedence, the rest of it has to be done first. That's why the right side of the expression of the statement gets performed first before it gets copied and across the equal sign and assigned into A. Am I going to expect you to memorize this whole chart? No, although one time when I was, applying for a job, I had to take a written exam, and I was supposed to know the entire operator precedence. And I didn't quite remember it. I didn't quite remember whether, these things were higher than that. So it's worth looking at this for a while. It helps, though, if you know what shifting is. Let's talk about shifting. We've talked about bits, right? Zeros and ones. Like we've talked about that. What that means, how we add those numbers up. Feel free to shake your head no. I'm not hearing any yeses. All right, we're going to have to do a lecture over bits. And since half the class is missing, that means that I can't just write on a whiteboard. All right, ultimately, computers just store zeros and ones in their little transistors, or burned onto the platter of a CD-ROM or something like that. And those are called bits. A bit is the smallest piece of information a computer can do, either a 0 or 1. Now for our computers to write stuff to memory or retrieve stuff from memory, they actually have to be pulled in clusters of bits. Kind of like if you have a minimum purchase from Amazon, right? You gotta get enough, to qualify for their free shipping. Well, to get the free shipping out of the computer, we have to have 8 bits. So 8 bits is known as a byte. And so, say we're going to hop in to our binary car. Binary is known as base 2, meaning we're using only bits to do our math. We only have 2 digits. Decimal is base 10, so we have 10 digits, right? 0 through 9. So binary is called base 2, using bits. It's a counting system where we only have 2 possible digits, which are 0 and 1s. Or combinations thereof, right? Because if you have decimal and you have the digits 0 through 9, you can chain as many of them together. You can write 999, right? Or 987365321, whatever. So if we hop into our decimal car, decimal is base 10, so it uses up to 10 different digits, 0 through 9, right? And if we count 0 through 9, that's equal to 10. Normally, if you tell somebody to count, they start counting at 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, but they left out 0. So if we were going to count off on our fingers, we really should start with 0, just like computers do. 0, 1, 2, 3, 4, that's one hand. 5, 6, 7, and 8, and 9, that's the other hand. And then and only then do we go over and let it roll over to a 10, right? I guess we start counting on our toes or something at that point. But school kids don't want to count like that. They want to start counting at 1. Anyways, so we're going to hop into our base 10 car. We're going to watch the odometer. We start off with a brand new car, 0, 0. We drive a mile, 0, 1. We drive another mile, 0, 2, 3, 4, 5, 6, 7, 8, 9. Now we really already are programmed in our brains since first grade or whatever to know what comes next. What comes after 9? 10, right? Okay, but technically what is happening? This digit has maxed out its possible value. It cannot go any higher than 9. So it gets reset back to 0. So it gets reset back to 0, and then the next place is incremented by 1. So that 0 becomes a 1. And then we start counting again, right? 11, 12, and so on, all the way up to 19. Here it goes again. We have maxed out this place. That's the 9. If we add 1 to it, it can't get any larger. So it has to reset back to 0, and we add 1 to the next place. Now what if we keep going and we get to 99? Well, if we only have 2 digits, we have a real problem. This one's maxed out, so it turns into a 0, and the 1 carries. Well, too bad. That one's maxed out too. And, bummer, we only had 2 digits on our odometer, so it rolled over. Just like if you had a car in the 70s and it had, you know, or 60s or whenever, and they only had 5 digits on the odometer, you could roll over your car at 100,000. Or if it had 6 digits, you could roll over your car at 1,000,000. I know you all have the idea. So at this point, we have overflow. We have exceeded the capacity of 2 digits. Now, of course, overflow doesn't happen as fast if you have 3 or 4 or 5 or 6 or whatever. But what about binary? We hop into our binary car. So we're going to do some binary counting. Start off at 0 again, 0, 1. Now, since binary only has 2 digits, it's all made out of zeros and ones, we have already exceeded the capacity of this place. Or we will if we go another mile. We can't go 0, 2 because binary is all zeros and ones. So just like with decimal, when you hit 9 and you need to go 1 more, this place resets back to a 0, and this one carries over, right? We add and carry, and we get 10. We go another mile. Now we've maxed it out, so if we went 1 more, that becomes a 0. We carry and add the 1. Whoops, that one becomes a 0 as well, and again we have overflow. Now, really, we don't do anything with 2-bit values very often. A byte is 8 bits, right? 1, 2, 3, 4, 5, 6, 7, 8, all the way up to 1, 1, 1, 1, 1, 1, 1, 1. So, you could say that this is a 0, and if we added all these up, if we treat them as unsigned, that's a 255. Well, how'd you figure that out? Well, how do we add them up? If we have the digits 491 in base 10, that means we have a hundreds place, we have a tens place, and a ones place. So 491. So what this really means is 4 times 100 plus 9 times 10, you see where I'm getting those numbers, plus how many ones do we have? It's right there, gang. Not a rhetorical question. How many ones do we have in the ones column? Just 1, right? 1 times 1. So that's equal to 400 plus 90 plus 1 is equal to 491. Now, lo and behold, we changed 491 to 491. Big deal. But this is the long expression of what we mean when we string more than 1 digit in a row. So, this is the ones place, this is the tens place, this is the 100s place. Now, where do these numbers come from? Well, we're in base 10, so the rightmost column is 10 to the power of 0, then the next one is 10 to the power of 1, and the next one is 10 to the power of 2, and so on. Now maybe you remember that 10 to the power of 2 means 10 squared. There's 100. Maybe you remember that 10 to the power of 1 is just that number all by itself, 10. And you probably don't remember, but there's a mathematical proof for it, that any number to the power of 0 is equal to 1, except maybe 0, right? 0 to the power of 0, I doubt that that's equal to 1. Let's type it into Google and find out. 0 to the power of 0. It's equal to 1 as well. What do you know? That's crazy talk, but it's true. So anything to the power of 0 is 1. So that's how we got these. These are place values. Another way to think about it is this number 0 here dictates how many zeros appear here, right? If there's no zeros there, there's no zeros there. If there's 1 0 there, there's 1 0 in our result. If there's 2 zeros here, there's 2 zeros in our result. So 10 to the power of 7 is a 1 followed by 7 zeros. Now 2's. We're going to do base 2. 101. 101 in base 2. Heck, let's carry it out to 4 digits. 1101 in base 2. Okay, so this is the 8's place, the 4's place, the 2's place, and the 1's place. Now where in the world did you get those? Well, this is 2 to the power of 3. 3. This is 2 to the power of 2. Okay, 2 to the power of 2. This is 2 to the power of 1. And this is 2 to the power of 0. Now we've already said that anything to the power of 0 is 1. And anything to the power of 1 is just itself. And something to the power of 2 is that number squared. And something to the power of 3 is that number cubed. You can tell it's just doubling each time, right? 1, 2, 4, 8. So the next one would be 16 and 32 and 64 and so on. It would just keep going up by doubles. So if we have these numbers here, 8421, and we're trying to figure out what 1101 is, if those are our place values and these are our digits, 1101, that's equal to 1 times 8 plus how many 4's do we have? 1 times 4. How many 2's do we have? 0 2's. And how many 1's do we have? 1 1. Now it's tedious to write out this 1 times 0 times and 1. So I don't mind if you just do this. That's equal to 8 plus 4 plus, well, there's no 2's in it, plus 1. And if we added those up, that's equal to 13. If you get this part right, I don't even care if you get that part right, right? You don't have to whip out your calculator and make absolutely sure that you got that right. As long as you have the 8 and the 4's and the 1's, as long as you have these place values correct, I would give it to you as a correct answer. So what if we had this? Well, that's a few too many, but we could do it. Let's do 8, since 8 is a byte. 1's place, 2's place, 4's place, 8's place, 16's place, 32's place. How many have I done so far? 6. Wait, 32, not 13. 16 doubled is 32. 64, 128. So let's space that out. All right, do we have any 128s? Do we have anything in the 128th column? Yeah, we have 1. I'm going to write it short form, and I'm just going to say 128. Plus, do we have anything in the 64 column? Yep. So plus 64. Do we have any 32s? Skipping that one. Do we have any 16s? Yep. Do we have any 8s? Sure do. Do we have any 4s? Nope, so I'm skipping the 4. Do we have any 2s? Yes. And do we have any 1s? No. So that's what it's equal to. That's enough, but just for curiosity's sake, I'm going to actually type that into Google and figure out what it is. Okay, 218. So what if it was all 1's? Then that would equal 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, which, if I copied and pasted it into Google, would tell me it was 255. There are 256 different possible values. We said the largest value is 255. Yeah, but you got to count 0, right? Just because your digits go up to 9, that's not only 9 digits. You got to count 0. So there's 10 different possibilities if your counting system goes from 0 to 9. How would you get 0 out of it? Well, what if the entire place was just all zeros, right? Then you wouldn't add up anything. There's nothing to add. And so that's equal to 0. So there's 256 different possibilities if you have 8 bytes. Bits. 2 bits. 1 bit gives you 2 possibilities. True or false, 1 or 0. 2 bits gives 4 possibilities. 4 bits gives 16 possibilities. I skipped 3. I shouldn't have maybe. 3 bits gives 3 possibilities, and so on. It keeps, 16, 3, 8. There we go. There's a formula for that. I guess if you have 0 bit, you only have 1 possibility. 0. Anyways, the formula is 2 to the power of the number of bits. So 2 to the power of n, where n is the number of bits. And so if n is equal to 1, 2 to the power of 1 is 2. If n is equal to 2, 2 to the power of 2 is 4. If n is equal to 3, 2 to the power of 3 is 8. 2 to the power of 4 is 16. And lastly, if you have 8 bits, 2 to the power of 8, you don't have that memorized probably, but 2 to the power of 8 is 256. So the largest value would be 255, and the smallest would be 0. Now these are all unsigned. What does unsigned mean? Unsigned means that it's always a positive number. It can never be negative. What if it had to be negative, right? Well, we need to do math sometimes that has negative numbers. Well, in that case, you use a signed value, which means that the first bit, if it's a 0, you treat the number as positive. But if the first bit is equal to 1, you treat it as negative. And so in that case, you can only go up to like 127, because you can't add 128 to it. But if you had 7 ones in a row, 64 plus 32 plus 16 plus 8, 4, 2, 1 adds up to 127. But you can also go negative, because if that gets set to 1, then you treat it as negative. Now I'm not going to show you how that's done. It's called 2's complement. Okay, so 2 to the power of n, where n is the number of bits, gives you the number of possible states, values, choices, values. So, back when you or your parents or whatever had an 8-bit good old Nintendo, it was an 8-bit computer. Or you had an Apple II or a Commodore, it was an 8-bit computer. So, your Nintendo, 8 bits. So, at the most, 2 to the power of 8 is 256, meaning that its screen could probably at most display colors that were one of a different 256 possible colors, right? One of them being black, one of them being white. And actually, it was a lot more limited than that. It was limited to like 8 colors per screen, but those 8 colors could be one of any 256, if that kind of makes sense. But once those colors were chosen, then that was it. So, right, the graphics were really crude. And also the number of pixels wide and tall were very limited. Their graphics cards were very limited. So if you bought your Genesis or you bought your Super Nintendo, they had 16 bits. So 2 to the power of 16 is a lot more. I think it's 65536, but I'm going to validate that. 2 to the power of 16. Yeah, 65536. Much more memory they could address. Yeah, because that's up to, it's actually known as 64 kilobytes. Where'd you get 64 from 65536? I'm going to kind of ignore that. It's 64K, 64 kilobytes. And each pixel on the screen could be one of 65,000 different colors and so on. So it's a much more powerful machine. That's why games on the Genesis and the NES look so much better than on the old Nintendo. Then you bought your modern computer with a 32-bit video card in it, or 32-bit memory addressing, running a 32-bit version of Windows or whatever, right? Windows 32. 32 bits. Okay, so what's 2 to the power of 32? It's about 2 billion. No, 4 billion. Wait, is that a billion? A billion is 9 zeros. 1, 2, 3, 4, 5, 6. Wait, it's not counting. It's not highlighting. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. So 2 to the power of 32 is about 4 billion. Or 4 gigabytes. So you buy your flash card, and your flash card is measured in gigabytes, right? You're going to stick this SD card in your camera, and it comes with 16 gigabytes, so it can hold a certain number of, photos. And you buy another card that might have 64 gigabytes or something like that. So anyway, that's great and all that, but your 32-bit laptop from the late 90s probably supported at most 4 gigabytes of RAM. So then they made 32-bit chips and 32-bit operating systems. Windows 64, vastly larger numbers. 2 to the power of 64. 2 to the power of 64 is a huge number. There's no way I can remember this. 2 to the power of 64 is a 1 followed by 19 zeros. Way bigger, right? So, your hard drives have to be able to support more than 4 gigabytes nowadays, right? You don't want your computers limited to only 4 gigabytes of RAM. So that's why they came up with, Windows 64 and 64-bit chips or whatever. So, and 65536 was pretty cool number of colors to display on the screen in the 80s. But after that, you wanted better stuff, and so PlayStations had better video cards, right? They could display, one of a million different colors, one of a billion, or whatever. Okay, so these also explain why certain data types can hold larger amounts of data. A byte counts up to a maximum value of 0, 0 to 255 if it's unsigned. A short is 16 bits. A byte is 1 byte, which is 8 bits, so it goes from 0 to 255. A short int is 2 bytes, which is 16 bits, so it goes from 0 to 65535 if it's unsigned. If it's signed, it goes up half as large, but it can also go negative. And so an unsigned int that's not short is 4 bytes long, so it's 32 bits, so it can hold up to 0 to 4 billion. Or negative 2 billion to positive 2 billion if it's signed. That's why we say that an int, if you're going to hold a value larger than 2 billion, then store it in some other kind of data type other than an int. And then there's long, a long int, or just a long int if you're using something other than Windows, which is 8 bytes. And we can see here that it holds really large values, a 1 followed by 19 zeros. Right. Ginormous. Ziga, Googa, trillion bytes, right? Whatever. Yeah, I just made that up, right? Ginormous value. You know, up to exponent 19. I don't even know how to say that. Just ginormous. Okay. So the more bytes that are dedicated to a specific variable, the larger the data can be. Hope that makes sense. Hope that makes sense. What I want you to do next is to pull out Notepad or pull up Word or any kind of editor. WordPad if you don't have Word installed, or TextPad if you're on your Mac, or whatever. You know, here's WordPad, but everybody has Notepad on their Windows machine. And so I'm going to ask you to do some conversions. Convert 111 in base 2 to decimal. And I'm going to do the first of these for you as well. And then do the rest of these. 1011, 0000, 1111, 1010, 0110, 0011. All right. So let's do the first one. I'm going to tack on a 0 here just to make it look 4 digits, just like the rest of them. Now the only way, whoops, 0111. The only way I can do this is by remembering the place values. What's the last one? It's a 1. The next one is a 2. The next one is a 4. The next one is an 8. So I'm just going to write those place values out like that. So what is 0111? Does it have any 8s? No. So I'm going to just hit the tab key, or you can put it underneath it or something. There's no 8s, but there is a 4. Huh? There is a 2. There's a 1. That's enough, but if you can actually successfully add them up and put the number there, so much the better. Now this one. Are there any 8s in this second number? Yep. So that's an 8. Are there any 4s in this one? There's no 4s in it? You were looking at the wrong one, no problem. Are there any 2s in it? Wait. Why did I type 4 there? There's no 4s in it. Are there any 2s in it? Yep. And are there any 1s in it? Yes, there are. And so if we added that up, that's equal to 11. Now 0, 0, 0, 0 is nothing plus nothing plus nothing plus nothing, so that's just equal to 0. Now I want y'all to do the next 4, please. Pause the recording. If you're doing this at home, go ahead and do it. All right, so then there's something called hexadecimal. Hexadecimal is a counting system. Hex meaning 6, like a hexagon. Des meaning 10. So 16 different choices. It's called base 16. And not only do you have the digits 0 through 9, right? If you were to count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, we have more digits, so we're not limited to 9. We can keep counting. So what they do, they just said the first 6 letters of the alphabet. Now if you were in Russia, the first 6 letters of the alphabet were different, so maybe they look different. But anyways, A, B, C, D, E, and F. Those are the 16 different digits. 16 different digits, which are 0 through 9 and A through F. So if we were counting them down, then a 0 is a 0, right? If this is our hex column and this is our decimal column, a 0 is a 0, obviously. A 1 is a 1, a 2 is a 2, a 3 is a 3, a 4 is a 4, a 5 is a 5, a 6 is a 6, a 7 is a 7, an 8 is an 8, a 9 is a 9. Ugh, that's a 10, that's an 11, that's a 12, that's a 13, that's a 14, and that's a 15. So, convert 10A3. Now that parentheses 16 means hexadecimal, or if you precede it by 0x. For some reason, that became the computer sciencey way. 0x means hexadecimal. 2 base 10. All right, we have different place values. We don't just have 1, 2, 4, and 8, or 1, 10, 100, and 1,000. Instead, we have 16 to the power of 0, 16 to the power of 1, 16 to the power of 2, and 16 to the power of 3. Now, if I remember, 16, anything to the power of 0 is a 1. Anything to the power of 1 is itself. Anything squared, I think 16 squared is 255, 256. And then the next one, 16 cubed, 16 to the power of 3, 4096. Those are our place values. 4096, 16, 256, 16, and 1. So we're going to convert 10A3 using those place values. 1, 0, A3. Then I'm going to make up another one. 0, A, 2, and F. I'm going to do the first one, and I want you to do the second one. Okay, the first one. How many 4096s do we have? We have just one 4096. So, 1 times 4096 plus, how many 256s do we have? Yeah, we don't have any. So 0 times 256. Or we could just delete that part, right? Plus, how many 16s do we have? Well, what did we say an A was? If we scroll up here, we said 10. So we have 10 times 16. Plus, lastly, how many 1s do we have? 3 times 1. Now, that would be enough to get full credit if I asked you to do the conversion, but 1 times 4096 is 4096 plus 0 there, plus what's 10 times 16? 160 plus 3. And just to double check to make sure I get it right, I'm going to paste that into Google. Like I said, if you get the first part of it right, I don't care if you actually do the math. 4259. Alright, so then I want you to do 0A2F. And just as a reminder, A is a 10, B is an 11, C is a 12, D is a 13, E is a 14, and F is a 15. Why am I telling you that? Because we have an A here, which is a 10, and we have an F here, which is a 15, and you're going to need those. So go ahead and do this conversion using these place values, just like we did up there. Alright, just for giggles, we're going to do one more. F, so I want you, if you're doing this at home, to fill in the answer here, right, for that one. 0A2F, just like we did here. I'll make this worksheet a little bit cleaner, make it easier to type along, and this will be the last thing we do. If we have 4096, 256, 16, 1, so if we have F, 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 that means F, since F means 15, 15 times 4096 plus 15 times 256, and you can be sure I'm going to copy and paste this into Google, plus 15 times 16 plus 15 times 1. Copy, paste. There we go, 65535. That looks familiar. I remember saying something about 65535. That was the largest value that you could hold using 16 bits. Your Sega Genesis could hold numbers between 0 and 65535. So that's enough bits and bytes. Let's make a Dropbox. Actually, I think, yeah, you could just copy your source code from your C++ file, from your C file, and paste it down at the bottom of this if you bothered writing those notes. If you didn't, that's fine. And I will write this up as a worksheet for the people to do at home. It's only a couple of conversions I actually made y'all do. Right, those 4. And then one more down here.